With an on-off controller, the final control element is either on or off. In other words, in some occasions, exist two. One is when the value is above the set point, and the other one is when the value is below the set point. An example of on-off controller is an on-off controlled liquid head system. In this part, if the liquid temperature goes below the set point, this is the set point, the steam valve opens and the steam turn on. If the temperature of liquids goes above the set point, the steam valve closes and the steam shut off. Here it's possible to understand better the behavior from an on-off controller. We can see an on-off control response in this picture. Here when the value is above the same set point, the final control element is off, and when the value is below the set point, the final control element is on. Now in this slide, we're going to talk about the depend in an on-off controller is usually a set point. The set point is 0. It's around that one, and it is a selectable value that determines the error range above and below. Above and below the set point that will not produce an output. It's like in the slide, the last slide. Here, it doesn't produce an output, only is on or off, on or off, off, on. Something like that.
Action and combination. Integral action or timed reset action. The integral action will cause the output and change the continuous to change until the error no longer exists. The amount of integral action is measured as repeats per minute. The derivative action responds to the speed at which the error signal is changing. That is, the greater the error change, the greater to correct output. The derivative action is measured in terms of time. Proportional integral (PI). PI control combines the characteristics of both types of control. A step change in the set point causes the control to the response proportionally, followed by the integral response, which is added to the proportional response to eliminate the offset error. Proportional derivative PT. Control is used in process control system with the errors that change very rapidly. By adding derivative control to the proportional control, we obtain a controlled output that responds to the error rate of change as well as to its magnitude.
A proportional integral derivative controller PID or PID controller or three-term controller is a control loop mechanism employing feedback that is widely used in industrial control systems and a variety of other applications requiring continuously modulated control. A PID controller continuously calculates an error value as the difference between a desired set point, or SP, and a measured process variable, or PV, and applies a correction based on proportional integral and derived terms, hence the name. In practical terms, it automatically applies accurate and responsive correction to a control function. An everyday example is the cruise control on a car, where ascending a hill would lower speed if only constant engine power here applied. The controller's PID algorithm restores the measured speed to the desired speed with minimal delay and overshot by increasing the power output of the engine. And proportional controllers are designed to eliminate the hunting or cycling associated with on-off control. They allow the final control elements to take intermediate positions between on and off. Proportioning action term permits analog control of the final control element to vary the amount of energy to the process depending on how much the value of the measured variable has shifted from the desired value. A proportional controller allows sector control of the process variable because its output can take on any value between fully on and fully off depending on the magnitude of the error signal.
The motion control is a system that provides the precise positioning, speed, and torque control for a wide range of motion applications. PLCs are ideally for rotary and linear motion control applications. An example is the figure 1, where is the displacement of an object through a mobile conveyor belt. The basic PLC motion control system consists of a controller, a motion module, a servo drive, one or more motors with encoders, and the machinery being controller. Okay, the role of each control component can be summarized as follows: PLC, motion module, and servo drive, which I will explain each one below. Okay, the PLC, the controller stores and runs the user program that controls the process. These programs contain movement instructions that control the movement of the axis. Once the controller finds the move instruction, it will now calculate the move commands to the axis. The aforementioned, we refer to the movement commands, the present position, and our speed of the servo motor. Okay, the next is the motion module. It receives motion commands for the controller and transforms them into a compatible form that the servo drive can understand. In addition, it updates the controller with the motor and drive's information, used to monitor drive and motor performance. The next is the servo drive. The servo drive receives the signal provided by the motion module and translate this signal into motor commands. These commands can include the position or speed. It also provides power to the servo motor in response to movement commands. The servo drive monitors the positions and speed of the motor by using an encoder mounted on the motor shaft. This feedback information is used within the servo drive to ensure precise motor movement. The servo drive takes us to the servo motor since it receives electrical energy that determines the speed and position of the motor shaft. In the figure 2, we can see that a filling motor must accelerate the filling mechanism in the direction in which the bottles move, equalize its speed and follow the bottles, while the figure 3 shows a 6-axis robot arm. Each axis of the robot arm is essentially a closed-loop servo control system.
In conclusion, the use of different types of controllers is quite important nowadays in the industry and in everyday life, although there are quite a few disadvantages in the application of them. So it is necessary to find which one best suits to it. For example, the on-and-off control is used recommended to use when the control doesn't need to be so precise.
A programmable logic controller or PLC specialized in the industry not only help improve performance but will support in different areas. For example, low labor cost because it automates process, improves process monitoring. The moment an error is detected, it can be stopped or corrected immediately. Savings in operation, maintenance, and energy costs, easy to use, for example, and many vendors include simple to use software when selling the control.
In conclusion, it's necessary to understand how the investigate terms work, since when waiting to control a system where this type of system are needed. We have to know what to use. For example, to have a Nicrom where a control is used that makes feedback with the temperature and the control turns the wire in the off for a special period to keep the temperature stable. With this type of control, you need to have a margin of error because given how it's work, the temperature fluctuates a few degrees.
The use of the PLC has become recurrent in the company since these machines generate a certain saving in question of time and efficiency since it is only programmed. However, there are sample processes, such in the case that stations are generated to be able to specify each job to be performed. On the other hand, I consider that the human being will always have contact with the PLC to maintain it or generate other programming to perform another function.